June 11th. This is video number 11. Drinking coffee again. It's a cup my daughter gave me from Bennett Springs. Has a trout on it. It's real nice. Anyway, yeah, it's like just a little bit after 10 a.m. I want to talk about a couple of different items today that are somewhat related because they're both about gravity, but there's pretty much separate items. One is Mercury's orbit. It's why it's perihelion precesses. The other is G-force, as in small g hyphen force. I'm going to go ahead and talk about Mercury's orbit a little bit first, get it out of the way, because it's actually the least complicated of the two. And once you understand this, it's not complicated. But hopefully I can explain it well enough so it'll take away some of that complication for people. Looking at Mercury's orbit, it's on my sheet, symmetry and motion. I showed this the other day, but I didn't show this little section on the right side of the sheet and up in the top corner. That's Mercury's orbit. If you look close, there's a depiction of the sun wobbling down toward one end of the orbit. That's where Mercury's perihelion is. There's two dots. They're supposed to be 1.56 degrees apart. That's the amount of precessing. What precessing means of Mercury's perihelion, all it means is that as it its closest distance advances in the same direction that the Mercury is orbiting, but it takes it 100 years for that to happen. Now the reason for that is not what Einstein came up with. Einstein apparently didn't know about sun wobble. I don't think scientists really knew the sun wobbled during his time. You can check that and correct me if I'm wrong, but I believe he didn't know about it. He died in 1955. Sun wobble has been, data has been collected on it for the past 50 years. I found some information on that a couple of years ago when I was working on this topic. The sun wobbles, but well, so does the Earth relative to the moon. But anyway, we don't want to go into that. Let's just talk about the sun. The planets are pulling on the sun so that it wobbles. I was going to show a couple of things in the book. I've got actually 4 pages in the book. Here's my book, Existence, Uniformity. It's got a picture of Iapetus, moon of Saturn, on the front. Brand new book. It's a good thing it was delayed. I was trying to get this published in September 2016, but and I made some improvements. Some of those improvements came in 2017 as I had more time to wait and consider things more thoroughly. This sheet is about sun wobble. I have several of these prints I made in 2015. One of them is that these are in the book. This is on sun wobble. I'll go ahead and tell you that this had to be rewritten from this part up in 2017. Here's the one on how the graph on how it's another sheet that I printed up in 2015 was giving out. I've been giving out as promos. They'd cost $4 a piece if I was going to sell them, but I haven't sold any yet. And my equation is in there that I've already mentioned in another video. This one talks about how fast how fast Jupiter and Saturn, say, would orbit at Mercury's distance, things like that. It has it plotted on the graph, the velocity. Here's symmetry and motion. It's in the book as well. There's a sheet on the fourth sheet as shows the experiment I did with large atoms that are attached to the small atoms that make up cotton fabric, the fibers, what those atoms look like lensing through direct sunlight, and how to interpret that in relation to what a realistic atom model would consist of. There are other things in the book. I was showing the book in an earlier take of this, and I like the way it go, but I said 366 degrees instead of 360 degrees. And I had another small mistake. Anyway, what I had mentioned is I got to redo all this because I like the way it went. I made a couple little errors, and now I'm doing it over. This is why galaxies spread out in the universe. I realized that in 2017, and this is how protons and neutrons are made. It explains right here, and that also explains why galaxies spread out. It's not because of a Big Bang exploded from a tiny speck, where everything doesn't have mass and it needs to get mass. That affected symmetry and motion as far as momentum, because those particles would need to have their own momentum for motion. It's not galaxies all surrounding us pulling everything out like I considered and wrote in the sheet Symmetry and Motion right in this section. I abandoned that when I realized what's causing galaxies to spread out, because there would have been no galaxies out there pulling on the particles that spewed out into space and then started to make protons and neutrons, etc., etc. So that's in red because there's a note in the book that shows why I had to change my mind on that. Also, in Barry Center and Sun Wobble, the sheet on that. In the book, this has all been rewritten in 2017, this section above here. I was rolling around a lot of different equations, trying different things in 2015, trying to figure out what in the world I thought was really going on. And I didn't quite have, the Sun Wobble is explained correctly. Everything here is correct now. But on the sheets that I've been giving out as a promo, this one, what was written in this section, it was when I was first trying to introduce the idea, and I was trying to introduce gravitational attraction as a pull force in newtons, and so I had something I was using for that, and there's something already in use that's much better, and so this has been reworked in 2017. I'm glad I had more time to get everything as good as it can be for my book. So a little bit about that. But Sun Wobble, the thing with Sun Wobble and Mercury's orbit is that the sun, when you look at the data on the Sun Wobble for the last 50 years, it doesn't look to have a repeating pattern. It probably does, but it may take more than 100 years for it to repeat. Or it may take 1,000 years for it to repeat. But it is jutting out. That's the whole thing here. And Mercury's orbit its perihelion may advance 1.56 degrees every the last 100 years. But it may advance 2.5 degrees the next 100 years, or it may advance 3 degrees or it may advance 1 degree the next one. So that would be depending on how much the sun wobbles and where Mercury's orbit is in relation to that jutting out. But the idea is that the sun juts out, Mercury's coming by in the direction it orbits, and it's pulled over a little bit because it's gravity is very time sensitive or time, distance sensitive, and uh, so when the distance is of the sun is less, especially at Mercury's distance, because it's the closest planet to the sun, then it's affected. The planets that are farther away, gravity dissipates over distance. It's much weaker. It doesn't affect them that much. So when the sun juts out, Mercury's affected. This perihelion advances, it precesses a little, and then the others aren't affected. And that's the true reason for why Mercury's perihelion precesses, not what Einstein came up with in his arcane equation for that. Um, okay, now I want to talk about G-force. Small g hyphen force. If you read in Wikipedia about relativity, one of the important factors that has caused people to adopt it the way they have is the idea that no g-force is felt on a planet, say, orbiting the sun, or say a moon orbiting a planet. It orbits, there's angular momentum, it's circling, it's maybe has a somewhat elliptical orbit, not perfectly circular orbit, and it's there's no g-force felt by any objects on the surface, whether those objects might be people or something inanimate. No. When you're driving down, like I mentioned in a previous video, when you're driving along in your car and you turn pretty sharply, you feel g-force. That's because your body isn't attached to the material in the car. I'm going to jump ahead a little bit here. When you have a body orbiting, it's tethered by gravity. Okay, that tethering in the case of the car turning is actually friction on the tires. And all of the solid material of the car is connected, and it's pulled over by that tethering of the friction of the tires turning. But your body is not attached to that. Your body is loose inside, and so you can feel the g-force. This tethering is also similar in the car, is also similar to, or this germane to the tethering in the centrifuges that train astronauts and pilots. The tethering in that case is whatever metal material is used, and the capsule that's being slung around at a high rate. Once again, the person is not attached atom to atom, molecule to molecule like the metal is. And so the person can, of course, we have our sensory systems, and we feel the g-force. And of course, you can black out if too much of your blood is thrown out and affects your circulation in your brain. So But the G-force is felt in those two situations, and both of those are material tethering, uh, just like the tether ball in a playground. There's a rope to a ball, and it's tethered, and you hit it, and it goes around and around. Um, the reason uh, a person or an object doesn't sense, there's no G-force sensed on a planet orbiting the sun or a moon orbiting a planet, even though there's attraction, gravity is the attraction of gravity is very much involved. Is well, let's just take the Earth for example. There's spinning of the Earth, and ever since we were born, we've been spinning. The spinning was established long before humans existed on Earth, and it evolved and arose on Earth out of the animalia that were present. But anyway, you've been spinning, and the spinning has momentum at all. Now, if you suddenly stopped, there's some way to stop that, which there isn't. You would, of course, feel it. It would be dangerous. But the spinning, as in the case of inertia or momentum, it's hard to get a body started to move, particularly a more massive, and then it's difficult to stop. And that's when G-force is felt, either when you start. That's why you have a kick from a shotgun or a rifle when you shoot it. It's starting. An object is being initiated. It's a velocity that's being initiated. If it's a high velocity, there's going to be more resistance. It's going to kick. The gun is going to kick against your shoulder. When it's slowing down, the same kind of thing. There's resistance. So that's when G-force is felt in both cases. But when we're spinning already, and we're spinning our entire lives on the surface of the Earth, that momentum is already established. We never feel it. But but something that's even more integral to this, and more important anyway, is, let's say, on the surface of Venus, a person or an object is standing. Of course, a person couldn't survive under that pressure, etc. But let's say if a person could, or let's say they're on the surface of Venus, and Venus is rotation, its spin is very, very slow. I forget now exactly what it is. It's not one revolution of its period, because if it were, then it would be tidally locked like the moon is with the Earth. There might be a couple of revolutions per period. I'd have to go back and double check that. But it's spinning very slow. It's spinning so slowly that you wouldn't even know it's spinning almost if you were on the surface of Venus. Now, when you're on the side of Venus in that situation, let's say, the attraction from the sun would be pulling on your body. But it doesn't lift your body from the surface of Venus, because the attraction from the body of Venus itself, given the range that you are on its surface and the amount of attraction force, is great enough to cancel out the attraction from the planet is great enough at that range, given the range you are away from the sun, to cancel the attraction to the sun. So the attraction from the sun is not felt. Okay. And it doesn't matter whether you're on the opposite side away from the sun or not. Always the attraction force at the surface of a planet that size is going to cancel out the attraction. And it would do so relative to other small bodies, even asteroids and comets. They would have enough attraction force to an object being, let's say, landed on a comet to hold it. and not be lifted away by attractions. There's your G-force that's not being sensed, and that's why. We don't need relativity to explain that either. Furthermore, the two types of tethering, I failed to stress this, the two types of tethering that there's a material tethering and there's a uh, gravitational tethering. And in orbits, the tethering is gravitational, so that contributes even more to G-force not being felt due on an orbiting body. Not only is the body significant enough to have its own gravity relative to objects that might be attracted to it, even down to objects as small as a comet, but that is inherently different than a material tethering in a centrifuge or that of a rope tethering of a ball and a tether ball, or the wheels, the tires of your car when they're turned, contact with the road, being a form of tethering that your thrust being loose inside, thrust to one side as your body wants to continue in a straight line essentially. And but when there's gravity, gravity is reciprocating with the entire planet or moon or comet or asteroid. It's whether it's to the sun or another planet or whatever. This is a more intrinsic or inherent reason why gravity or G-force isn't felt in an orbiting body. Those particles are the atoms and molecules that are essentially compressed together by gravity, particularly as you get down deep into the material. There's loose objects on the surface. There might be an atmosphere above those loose objects on the surface, but then it's also being held in by gravity. But in the body itself, that is compressed by gravity, its own gravity within the body, all of those particles, atoms, and molecules that are essentially connected, they are tugged together. They are tugging collectively toward the sun or whatever primary is being orbited, and that attraction and that collective attraction is not present in a centrifuge or with a tether ball or when you're turning in your car or when you're braking in your car. The tethering is different, and the G-force is not going to be felt when in orbiting bodies, primarily for that reason. There are other details involved, like I've already explained, but that's inherently different than a material tethering. I wanted to clarify that a little bit more. One more note probably needs to be made about this is that there's such a thing as tidal heating. Now, tidal heating isn't what causes the core of a planet to heat up. That's caused by compression. And I've explained that in other places. I won't go into that now, but tidal heating looks like a true phenomenon. You've got on the Earth, the moon is causing tides in the ocean. What you would need to have with tidal heating, if let's say a body is orbiting Jupiter, one of its moons, and relative to the direction of Jupiter, its interior is weak enough at certain points so that movement can be caused. Well, movement creates friction. Friction creates heat. So the tidal heating concept looks like a valid one. Probably does. Probably does most definitely occur, but it's not what's causing lava in the core of a planet, molten material, liquid, rock, and metals, and all of that. If that's why it was invented, that's a mistake. But as far as further out in a moon or a body where the material can flex, gravity could definitely cause that. I buy into that.